Today we have a pleasure of attending the talk by Shi Li. She studied undergraduate at Tsinghua University, then he did PhD at Princeton. Then he had positions at Toyota Technological Institute in Chicago, Buffalo University, and now recently moved to Nanjing University. She won several awards for exceptional teaching and research, several best paper awards in high-profile conferences such as Fox, ICALP, and so on. So today we have the pleasure of having him as a speaker. Thanks.
Okay, thank you for the introduction. So can you hear me good? Okay, and so I'm going to talk about online unrelated machine node balancing and generalized flow with recourse problem. So this is based on joint work with Ravi Krishnaswamy and Varam Suryanarayana. So Ravi is from Microsoft Research India, and Varam is a student in Cornell University. I was a professor at University of Buffalo, and recently I moved to Nanjing University. Okay, so let me start with the introduction of the problem. So the problem we are considering is the unrelated machine node balancing problem. And this is a classic problem in scheduling theory. And we first describe the problem in the offline version. So we are given everything at the beginning for the problem. So in the problem, we are given, we are given a set J of jobs, a set M of machines. We have N jobs and M machines. And for every machine I and the job J, there is a processing time, Pij. So that indicates if we schedule job J on machine I, it takes Pij units of time to process the job. Then the goal of the problem is to assign jobs to machines so as to minimize the maximum load over all machines. Sometimes this maximum load is also called the max span. So that is the maximum over all machine I and sum of jobs J assigned to I, Pij values. So for example, for this instance, if we assign jobs in this way, then the nodes of the machines are 14, 8, and 13, and then the maximum load is 14. And this is the value we try to minimize. Okay, so is the problem definition clear for the offline version? But the problem we are interested in is the online version. So in the online version, jobs arrive one by one. And when a job arrives, we are given its Pij values. And, but once a job arrives, we have to decide immediately which machine we assign the job to. So once we decided the machine that the job is assigned to, the decision is irrevocable, and we cannot change it in the future. So we know those are the machines at the beginning. Then the first job arrives. We know those are the processing times. So when there is no edge, we just assume the job cannot be assigned to that machine. Or in other words, the processing time is infinity. Okay, so then maybe we decide to assign the job to this machine, and this job comes, we decide to assign the job to this machine, and so on. And then we need to, again, minimize the total, the maximum load over all machines. The setting is the same. The only difference is that the job arrives one by one. We have to make a decision for each job immediately after it arrives. Okay, so this is the online version. So notice that it's better, more convenient to consider the problem as a node balancing problem instead of a scheduling problem. So if you think of it as a scheduling problem, there is a notion of time in the scheduling problem. That might be confusing because the online algorithms also we have a notion of time. So we just assume there is a notion of time, but time 1, the first job arrives, time 2, the second job arrives, and so on. Or you can think of it as a scheduling problem, but this is the pre-scheduling step. So the whole algorithm is for the pre-scheduling. Once the scheduling is decided, then we process the jobs after the algorithm ends. Okay. So what do we know about the two versions for the problem? Offline version and online version. So for offline version, we talk about approximation ratios. So those are the algorithms that run in polynomial time, but we hope to optimize the ratio between the solution we got and the optimal solution. And for the offline version of the problem, the best known approximation ratio is 2. This is a non-standing state-of-art result. And on the negative side, we know we cannot. What?
It should be lens thrust noise and
Oh, sorry. Yeah, that's a mistake. Okay. Yeah. So on the negative side, there is a hardness of 1.5. So that means if P is not equal to NP, we cannot do better than 1.5 approximation. So there is a long-standing gap between the upper bound and the lower bound. And it's a big open problem whether we can reduce the gap. Okay. Then for the online problem, we talk about competitive ratios. And the status is better. So we have a better understanding of the problem in the online setting. So we have a tight order log m competitive ratio for the problem. So that means we have an algorithm that achieves order log m competitive ratio, and there is a negative result showing that you cannot do better than this. Okay, so we are focusing on the online algorithm in this talk. So then you might ask, so the problem is solved. What are we looking for now? Well, so this is the question that motivated our research. So what if in the online algorithm, we are allowed to change the assignment of jobs a few times? So maybe in practice, it is expensive to switch the jobs from one machine to another machine, but it's not prohibitively expensive. So maybe we are still allowed to change a few jobs, but we don't want to change too many times. So that's the motivation. We are allowed to reassign jobs to new machines a few times, and the number of times we reassign jobs is called the recourse of the algorithm. So there is a total recourse. The total recourse of the algorithm at time t is just the number of times we swap jobs, or we reassign jobs by time t. Okay, question?
Is there a kind of really compelling example of an application where you have to schedule the tasks online before you run the machines?
Maybe think of it as the load balancing problem. If you want to store a file on the server, maybe it's not very good to move the files from one server to another, but you can do that. And the objective is you want to minimize the load at each server.
I'm just wondering about the online constraint in the first place.
Yeah, online constraint, maybe files, they come one by one, right? Once a file comes, you have to decide to put it on the server.
But you don't do anything until they've all arrived, and then you put them all on the server?
For the load balancing application, yeah, you don't do anything. For example, this server, maybe the performance depends on the load of the server. If you have a huge number of files, the total size of the files on the server is big, maybe it affects its performance. Yeah, that's a better application. So for scheduling, maybe you say that you have to decide the scheduling before some time point. You don't want to make too many changes, but after that point, you cannot make changes, then you just process the jobs. Okay, question?
So
Okay, maybe the next one, okay. Okay, so it's more convenient for us to use amortized recourse by time t. So the amortized recourse by time t is just the total recourse up to time t divided by t. So notice that this time t means t jobs have arrived. So time 1, the first job arrives. Time 2, the second job arrives. So this is basically the number of job changes per number of swaps per job. But it's the average things.
It happens sometimes.
Okay, no problem. Okay. Yeah, it's the average across all jobs. Maybe some jobs you swap it many times, but some other jobs you swap them a few times. On average, we want the number of times to be small. So that's the amortized recourse. Okay, so what do we know about this new problem, the online node balancing with recourse problem? So prior to our result, the only result is this result due to Gupta et al. They showed that if you allow a constant amortized recourse, then you can achieve log mn competitive ratio. So in this talk, you should think of the case m is polynomially related to n. So log mn is just log m or log m. There is not much difference. And remember that if we don't allow any recourse, then you can only get a log n competitive ratio. So the result shows that if you allow just O1 recourse, you can do exponentially better. So O1 recourse means on average, every job is swapped constant number of times. Okay. However, their algorithm also works only for the restricted assignment model. So it does not work for the general unrelated machine model. So what's the restricted assignment model? It's a special case. So where every job, the Pij value is either a Pj or infinity. So that means for every job j, there is an intrinsic size Pj for the job. So if the job can be assigned to one machine, then its processing time on that machine is Pj. Or it cannot be processed on that machine, then Pij is infinity. So for this special case, you can just use a vector of Pj values, one for each job j, and the bipartite graph to denote the instance. While for the general unrelated machine scheduling problem, you need a whole matrix. Okay, so their algorithm only works for this restricted assignment model. So here comes our result. So we gave 2 results, and again, the paper is joint work with Krishna Swami and Suryanarayana, and it will appear in the upcoming talk. So first, we show that we can achieve a 2 plus epsilon competitive ratio if we allow slightly more than constant recourse, so order log n recourse. So for every job, we swap it order log n times. There is a dependence on epsilon, but in the talk, I will ignore the dependence on epsilon for now. And our algorithm works for the general unrelated machine model. And the second result asks, what if we are only allowed to use O1 recourse? So that is, if every job you can only swap it a constant number of times, well, we show that we can still do better than the result of Gupta et al. The improvement is tiny. So we improved the competitive ratio from log mn to log n over log n. So it's only by a log factor, but it's still an improvement. Okay, question?
The competitive ratio, what are you comparing against? Is it the completely optimal allocation or the...
It's the offline optimum. So offline optimum knows everything ahead of the time. So it fixed the schedule by that time, and we are comparing our online schedule the makespan against the makespan of the optimum schedule. Yeah, it's very unfair to the online algorithm. That's why on the negative side, even if you don't assume any complexity assumption, you can prove very strong lower bound. Yeah. Okay, questions? Other?
Are you assuming adversarial arrivals of the jobs?
Can you say that again?
Are the jobs arriving in an adversarial manner? Is this what you're assuming? Or you're assuming that the jobs arrive in a random fashion?
Yeah, the question was, do we make any assumption on the arrival order of jobs, right? Yeah. No, we don't assume anything like that. It's arbitrary, so anything can happen, yeah. Other questions? Okay, then I'm going to move on to talk about the two results. So both results are based on LP relaxation, so linear programming relaxation. So we solve the linear programming relaxation for the instance online, and then we round the LP solutions online. So in the first step, we solve the LP relaxation online. That means at every time we have an instance, we need to output an LP solution for the instance for every time. Then in the rounding algorithm, we are given the instance at that time, but we are also given the LP solution at that time. We need to round the LP solution to the integral solution. Okay. So then we need to first talk about how do we construct the fractional solution online, or the linear program solution online. Okay, throughout the talk, I'm going to make an assumption that will be convenient for us. So we assume there is a target makespan T, and then our goal is to compare our makespan against the target makespan. So we are promised that at any time, the optimal solution has makespan at most T, and if we want to achieve alpha competitive ratio, then our schedule can only have makespan alpha T. Okay, so this assumption can be made with a small loss in the recourse. So it's a constant loss in the recourse. Okay, so because of this assumption, then we can assume Pij is either in 0T or infinity. So if Pij is more than T but not infinity, then we know in the optimal solution, you won't assign this job to this machine. So this will be convenient to design, for designing our algorithm. Okay, so once we have the assumption, then we can describe the linear programming relaxation for the problem. So far, we focus on the online version of the problem. And the LP relaxation is very natural. So Xij will indicate whether job j is assigned to machine I in the integer program. Okay, but in the linear program, Xij can be any number between 0 and 1. So it's the fraction of job j assigned to I. And then the first constraint requires that for every job j, the total fraction of job j assigned to machine I should be 1. So we should assign the whole job j to machines. The second constraint is for the node of machines. For every machine I, the node should be at most t, the fractional node. So Pij is the processing time of job j on I. Xij is the fraction of the job assigned to I. Then finally, all the variables should be non-negative. Okay, so that's the LP relaxation for the problem. But in the online setting, we need to output a LP solution at every time. So here we use Xij to denote the value of Xij at time t. Also, we assume that if at time t some job has not arrived, then Xij for that job is always 0, just to make sure the notation is good. Okay. So we output a fractional solution at any time t, then we hope that the fractional solutions do not change too much from time to time. Okay, so this is measured by the fractional recourse over the time. So what's the fractional recourse? So it's the fractional recourse at time t is just the LP solution, the L1 distance between the solution at time t and at time t minus 1. So you just take sum up over all pairs ij and the absolute value of xijt minus xijt minus 1. So that's the fractional recourse of the solutions. But it's more convenient to use this red quantity. So up to a factor of 2, this is at most this quantity. So in this quantity, if xijt is more than xijt minus 1, we count it towards the recourse. But if it's smaller than xijt minus 1, the recourse is 0. So we only count the increment of xij values, is not the decrement. So up to a factor of 2, they are equivalent. Okay, so that's the fractional recourse. And our goal is to construct good fractional solutions over time with O1 amortized fractional recourse. Okay, again, amortized recourse is just the total recourse divided by t, or divided by the number of jobs arrived so far. So by time t, t jobs arrived. That's our goal. Question so far? What's our goal for constructing the fractional solutions? So at any time, we need to construct a fractional solution, but over the time, the total change of the fractional solutions is small. Okay. So to do so, we reduce the problem to the online network flow problem. Okay, so what's online network flow problem? So we are given a graph, and this is almost the whole graph, but it only contains one sink. We have many sources. The sources will arrive one by one. And so each edge in the graph has two parameters. One is the capacity, one is the per unit cost. So that's just as in the typical network flow problem. So capacity means that you can only send so much flow across this edge. Then cost CE means if you send 1 unit flow across the edge, you need to pay CE. Okay. The online feature is as follows. So at each time, one source arrives. So source S1 arrives. Then we are given the outgoing edges of S1, and the outgoing edges are to the existing graph. So sources do not have incoming edges. And we are also given a parameter A1, and then we need to send A1 units flow from S1 to tau. And we have to send the A1 units flow immediately. Then the next time S2 arrives, and we need to send A2 units flow from S2 to tau. Then we need to send A3 units flow from A3 to tau. But we are allowed to decrease the flow values. So for example, here to send some flow from S3 to tau, we can send the flow from S3 to this vertex, then send the flow backwards. That means decrease the flow values of this edge, and then send the flow from this node to this node, then to tau. So this is exactly the same as the augmenting passes. So this is the online problem. But what makes the online problem different from the offline problem is the following. So if we have the offline algorithm, we consider the cost. So how does the cost change? So if we increase the flow value of some edge by theta, then the cost will increase by theta CE. But if we decrease the flow value by theta, then the cost will decrease because the flow value decreases, right? Then if you wanted to solve the network flow problem optimally, you can just keep looking for the cheapest augmenting passes. So that's the algorithm. So that's the offline algorithm. However, in the online algorithm, the definition of cost is different. So if you increase the flow value, you are going to still pay for the cost. But if you decrease the flow value of the edge, you don't get a decrement in the cost. So the cost will be 0. Okay, so if you decrease the cost, decrease the flow value, you don't save the cost. So that means if you have an edge, you keep increasing and decreasing the costs, decreasing and increasing the flow values, the cost, you will incur a huge cost. Okay, so that's the definition of the online problem, online network flow problem. Then the cost of the online algorithm will be this. So the sum over all time steps t, sum over all edges e, ce times the increment of flow values of e from time t minus 1 to t. So if it's positive, you have a cost. If it's negative, this is 0. You don't get a negative cost. Okay. Then Gupta et al. Showed that you can solve the online network flow problem. So the cost of the whole algorithm will be order 1 plus epsilon times C star, where C star is the optimal offline cost for the offline problem. So it's just a static instance. We consider the whole instance up to some time point. We have all the sources. For the sources, what's the optimal cost to send those flow to the sink? However, they need to violate the capacities by a factor of 2 plus epsilon. So if this edge, you can only send CE unit flow in the problem definition, but their algorithm will send 2 plus epsilon times CE. So they need to violate the capacities by 2 plus epsilon. Okay, so next I'm going to show why can we reduce the construction of fractional solutions to the network flow problem. So this is not hard. So we construct the following graph instance. So the left side contains the jobs, the right side contains the machines, then there is a supersync tau, and the edges are defined as follows. So if there is so consider job J and machine I. Suppose job J can be assigned to machine I, then we add an edge from job J to machine I. The capacity of the edge is infinity, and the cost will be 1 over Pj. So if you have to send Pj units flow from job J to tau, then you need to scale the cost by 1 over Pj, right? So in the original problem, we need to assign job J by a fraction of 1. But it's more convenient for us to use the volume of the jobs. So the job J has volume Pj. We need to send the Pj units flow from J to tau. But the Pj units of flow, the total cost is just 1. Because the recourse is defined by how many times we change the job. If you change the whole job from one machine to another machine, the cost is 1, but you have volume Pj, so that's why we need to scale the cost. So the cost is 1 over Pj. Okay, so it's easy to see the equivalence between the construction of fractional solution for the scheduling problem online and the online network flow problem. The two problems are equivalent. Okay. And however, you can see that this uses the restricted assignment model. So it heavily uses that all the Pj values are the same, because you can only scale the job J by the same factor Pj. So if J is assigned to this machine I, the processing time is Pij, and for another machine I, the processing time is different, then the reduction does not work, right? Okay, so what we do to address this issue, what we do is we generalize the network flow problem to the generalized network flow problem. Okay, I'm just to give just a rough idea about the definition of the generalized network flow problem. So in addition to the two parameters, capacity and per unit cost, we have one more parameter for every edge E. It's called the gain, so gamma E. So what does gamma E mean? So if we send theta units flow from the sender side of the edge E, then the receiver side of the edge E will receive gamma E times theta units flow. So gamma E could be smaller than 1, could be bigger than 1. If it's smaller than 1, then the flow will decrease. And if it's more than 1, it will increase. So if gamma E is 1 for every edge E, that's just the normal network flow problem. Okay, so that's the generalized network flow problem. Other than that, so everything is the same as the online network flow problem. So S1 comes, we need to send some flow from S1 to tau. And S2 comes, we need to assign some flow from S2 to tau. It's still the online problem. Okay, so what we can do is we can give an algorithm for the general version of the network flow problem. We get the same cost ratio. Moreover, we improve the capacity violation factor from 2 plus epsilon of Gupta et al. To 1 plus epsilon. Okay. And the algorithm is indeed very natural. It's just the offline algorithm. So every time we find the cheapest way to send 1 unit flow from the source to the sink. So we just assume so every source we just need to send 1 unit flow. Okay, so it's just equivalent to the offline algorithm. Every time we send the flow using the cheapest way. But the definition of the cheapest way is slightly different. In the offline algorithm, when you decrease the flow, you save the cost. But in the online algorithm, when you decrease the flow, you don't save the cost. You don't pay for the cost, but you don't decrease the cost. But there is, again, you can define what is the cheapest way to send the flow. Okay, at any time, you just use the cheapest way to send the flow, and you repeat. And we can show that the cost of the whole algorithm is bounded by order 1 over epsilon times the cost of a dual solution for the network flow instance. Then the dual solution will be bounded by the optimal offline cost. However, the dual solution is only valid for the instance where the capacities are scaled by 1 over 1 plus epsilon. So that means we compare the cost of our algorithm against the cost, offline cost of a harder instance. So in the offline instance, we scale the capacities down, so it's a harder instance. The cost could be bigger, and we are comparing our cost for easier instance against the offline cost for a harder instance. So that's called a bi-criteria approximation. Okay, questions so far? Yeah, it's just the rough idea of the algorithm. So we reduce our LP solving algorithm to the generalized network flow instance.
What was the difference in the Gupta et al. Approach?
Yeah, Gupta et al. Approach is indeed, so let's focus on the restricted assignment model, the non-generalized model. The only difference, maybe the main difference, is that in our definition, when we decrease the flow, we don't incur cost. So the cost is 0. But in their definition, they say that, okay, even if you decrease the flow value, you need to pay a cost. So if you decrease the flow value by 1, you pay a cost of 1 times CE. So that's the reason why they can only get 2 plus epsilon. We show that, hey, if you define the cost in our way, you can improve the capacity violation from 2 plus epsilon to 1 plus epsilon. So that's the main improvement, but also we generalized their result from the network flow to the generalized network flow. Okay.
The reports is also using a dual certificate.
Yeah, a dual certificate, yes. Okay, then let's move on to the rounding algorithms. I think I only have time to talk about one rounding algorithm. So I'll talk about the first one. So that's the 2 plus epsilon approximate online rounding algorithm with order log n amortized recourse. So recall the setting. So we are given the scheduling problem online. So every time one job arrives, we have to assign the job immediately. But now we are also given a fractional solution at each time. So at this time, I have a fractional assignment of jobs to machines. Next time, I have another fractional assignment of jobs to machines. And the fractional solutions have a small recourse. So they don't change too often, right? The sum of L1 distances is small. Then we need to use the fractional solutions, and we round them to integral solutions. Okay, so this is what a fractional solution looks like. So we have jobs, we have machines, and every job can be assigned to every machine here, and the xij is the fraction of a job j assigned to machine I. If you look at every job j, the sum of xij values is 1. And if you look at every machine I, the sum of pij, xij is at most t. Right? This is what we get at each time step. So then we are going to talk about the offline rounding algorithm of Simoes Tados that achieves the 2 approximation. We are going to use that as our baseline. So at every time, we are going to run that algorithm, but we need to make a small modification to this algorithm to make sure our recourse is small. Okay, so what is this 2 approximation rounding algorithm? So far we are focusing on the online or offline problem. So we are given the whole instance, and we are given a fractional solution. We need to round it to an integral solution. Okay, so we will construct another bipartite graph. So notice that this bipartite graph is between jobs and machines. The new bipartite graph is between jobs and the sub-machines. So every machine I, we will divide it into many sub-machines. Okay, so let's just focus on one machine I, and we have, say, 5 jobs are assigned to machine I positively, and the fractions are xj1, xij1, xij2, xij5. Okay, and we also sort the jobs in decreasing order of processing times. So that is J1 is the biggest, J2 is the second biggest on machine I. So how do we construct the sub-machines for machine I? Well, we first construct many job intervals. So each vertical line here is a job interval. So for job J1, we have a job interval of height xij1. So that's the job interval for job J1. Then for job J2, we have a job interval of height xij2. And we stack all the job intervals together from top to bottom. Okay, those are the job intervals. Then on the right side, we will create sub-machine intervals. So each sub-machine interval will have length 1. So this is sub-machine I1, sub-machine I2, sub-machine I3, sub-machine I4. So every sub-machine will correspond to a segment of length 1. So we will create as many submachines as possible so that the number of, so that the whole interval will cover the job intervals on the left side. So that means if the total length of job intervals is, say, 3.5, then you need 4 segments. Okay. So then we have 4 submachines for machine I. And this will give us a bipartite graph between the 5 jobs here and the 4 submachines. And it also gives us a fractional assignment of jobs to the submachines. Remember, on the left side, we have a fractional assignment of jobs to this machine I, but now it's between jobs to the submachines. And how are the assignment values defined? So if you look at job J2 and the submachine I1, then by how much should we assign job J2 to submachine I1? Well, we look at the intersection of the interval for job J2 and the segment for I1. So this is the segment for I1. This is the interval for job J2. There is an intersection. Then the fractional assignment will be the length of this intersection. So you can see that J1 will be assigned to I1 only. J2 will be assigned to I1 and I2 positively. J3 will only be assigned to I1 and so on. So that's the definition of the fractional assignment. Then you can see that for every job here, the total fractional assignment is precisely its x value, right? The x J1 will be assigned to the submachines with a fraction of xij1. And every segment, the total fractional assignment it gets will be at most 1. Indeed, it's 1 except for the last submachine. So here it gets 1 fractional job, 1 fractional job, 1 fractional job. Okay, so this is how we define the submachines for machine I and how we assign the jobs to the submachines. So in the input, we only know the assignment from jobs to machines, but now we have assignment from jobs to submachines. And we do this for every machine I, and so we get an assignment of jobs to the submachines over all machines, but that fractional assignment defines a matching between jobs and submachines. So every job is assigned by an extension of exactly 1, right? Every job is fully assigned, so the sum of xij values is 1, and every submachine gets a fraction of at most 1. So if it's the last submachine of the job, last submachine for a machine, the fraction may be smaller than 1, otherwise it's exactly 1. So this is a fractional matching between jobs and the submachines. Then we can just use an integral matching algorithm to find the integral matching in the support of this bipartite graph, and that gives us a matching. It gives us an assignment of jobs to machines, and it turns out that any such integral assignment will have maximum node at most 2t. So 1t comes from the fractional node t. The other t is just the maximum job size is t. So every machine, you make it a t from the fractional solution, but there is one special job, and that special job will have node t on machine I. So in total, you get 2t. So that's the 2 approximate rounding algorithm from Simoes and Tados. Okay, so that's the offline algorithm. And now we want to run the algorithm online. So notice that at every time, we have a fractional solution. So what if we just run the fractional solution using the algorithm of Simoes and Tados? So at time 1, we have a fractional solution. we run the 2 approximate rounding algorithm, we get an integral solution. And at time 10, we have a fractional solution. We run the algorithm of Simoes and Tados, we get another solution. We just output all the solutions. What's the issue with that algorithm?
The assignments could change a lot.
Yeah, the assignment could change a lot. Why is that the case? Imagine this is the assignment of jobs to the sub-machines of machine I. So what if we just increase xij1 by epsilon, tiny, by a little bit? Then all the intervals below j1 will be shifted downwards, right? If you just create segments of length 1, the whole bipartite graph between jobs here and the sub-machines of I will change. Even if you just change the first interval a little bit, the whole bipartite graph might change. So what we are going to do is we design design another algorithm that's insensitive to small changes. Okay, so that if you just change xij a little bit, then the graph structure does not change too much. Then in our integral matching, we don't need to change too many edges. So how do we do that? Well, we use a 2-level partition of the horizon, so the union of the intervals. So first, we create buckets of length between 1 over epsilon and 4 over epsilon. Then each bucket will be divided into segments of length between 1 minus epsilon and 3 minus epsilon. So for now, you can forget about the buckets, only focus on the segments. So segments will have length between 1 minus epsilon and 1 minus 3 epsilon. So there is a flexibility, there is a buffer between the upper bound and lower bound. Now imagine that if my segment, the length is 1 minus 2 epsilon, is something in between 1 minus epsilon and 1 minus 3 epsilon. But now I increase xij by, say, epsilon over 10. Then I don't need to change the graph structure. Why? I can just increase the segment by epsilon over 10. So this job interval increases, and then we also increase the length of the segment. So the length of the segment increases, and then the relative relationships between the job intervals and the segments, they don't change, right? Okay, because we have a gap of 2 epsilon, that gives us the flexibility so that we don't change the bipartite graph that much. So that's the idea. And again, we have one segment. For every segment, we create one submachine. But the only difference is that every segment, the length will not be 1. It's between 1 minus 3 epsilon and 1 minus epsilon. And that can change during the algorithm so that we don't change the bipartite graph that often. Okay, here is the rough idea why we can have a small recourse if we apply this 2-level partitioning. So the buckets will have size between 1 over epsilon and 4 over epsilon. The segments in each bucket will have length between 1 minus 3 epsilon and 1 minus epsilon. Okay, so whenever you have a fractional recourse, it corresponds to increasing or decreasing the length of some job interval. But if you increase the length of the job interval or decrease the length of the job interval, on the right side, we also increase or decrease the length of the corresponding segment so that the bipartite graph does not change, right? If this is the job interval, this is the segment, we increased it a little bit, we also increase the length of the segment a little bit. But we have to maintain those properties. So each segment, the length will be between 1 minus 3 epsilon and 1 minus epsilon. And each bucket, the length will be between 1 over epsilon and 4 over epsilon. So here is what we do in case some bad events happen. So if the bucket, the length becomes more than 4 over epsilon, that's not allowed. So what we do is we just divide the bucket into 2 buckets. So each bucket will have size 2 over epsilon. So 2 over epsilon is okay. So it's between 1 over epsilon and 4 over epsilon. And if the length of a bucket drops to 1 over epsilon, we merge it with the previous bucket. But if the merged bucket, the length becomes more than 4 over epsilon, we divide it into 2 buckets. And if the segment changes, the length of one segment changes to 1 minus 3 epsilon or 1 minus epsilon, we just redivide the whole bucket into segments of length 1 minus 2 epsilon. So 1 minus 2 epsilon is just in the middle, so that if we applied this redividing operation, then it takes a long time for us to redivide again. Because if you wanted to change from 1 minus 2 epsilon to 1 minus 3 epsilon or 1 minus epsilon, you need an epsilon fractional change, right? So that's the reason we choose the middle number, 1 minus 2 epsilon. Okay, so why is this good? First, this 1 minus theta epsilon segment length will guarantee that in the bipartite graph, the augmenting paths will have small length. It will have order log n length. Okay, so that's just the expansion argument. If we have a 1 minus epsilon slack here, then the augmenting paths will have short lengths. On the other hand, the bucket has size order 1 over epsilon, and then we know that the last segment in the bucket could be very short, right?
Would you argue that the residual graph is expanding?
Not expanding argument. So if you go one step, this is the number of vertices you can reach in the residual graph. If you go 2 steps, it will increase by a factor of 1 plus epsilon. Then overall, in order log base 1 plus epsilon n steps, you will reach the whole graph. Okay. Okay, so that's the reason we choose 1 over epsilon to be the size, the length of a bucket. So it's not too small and it's not too big. Okay, so I think I don't have time to talk about the second algorithm. So I will just sum up the talk. So we gave improved algorithms for online unrelated machine with recourse problem. So we achieve an algorithm with 2 plus epsilon competitive ratio using order log n amortized recourse. And if we only use O1 amortized recourse, then the competitive ratio is log n over log n. That's a small improvement over the previous based ratio. And on the way of designing the algorithm, we give an online algorithm for the generalized network flow problem. Okay, thank you.
Thank you for the great talk. And now questions.
Okay.
So it's a kind of model question. So as far as I understand, the competitive ratio you are measuring is the worst case at any instant in time versus the offline optimum. Is that correct? So you're running this online algorithm.
Yeah, first let's just fix the time. So we only focus on time 100, but you don't know this time 100 at the beginning. So the adversary can say, okay, stop here. This is the offline optimum. This is your max span. What's the ratio? And since you don't know the time, you have to maintain a small ratio at any time.
Okay. Good. So I guess my modeling question was, what if you have something like a non-terminating algorithm? So to give a concrete application, the jobs are people uploading YouTube videos to the cloud, through Google Cloud, and the machines are Google's data centers.
Okay.
And there is no fixed horizon for this. You know, it can keep running for
forever.
decades,
Yes.
decades, forever. And now we don't have well, you could use your same notion of offline optimum. That is, you stop it at any time t and compute the offline optimum there.
Yes.
So it would, even in this setting, you will get the same ratios.
Yeah, we get the same ratio, yes.
Oh. Yeah, thanks.
Okay, other questions? Okay.
So can you say briefly, like, how do you get that log by triple log? Like, what's the...
Okay, so we use an offline algorithm. So the offline algorithm will roughly do the following. So we have machines, 2 jobs, and we say a job is small if the Pij value is less than t over log n, big if it's more than t over log n, and then a job is small if half a fraction of it is assigned to using small edges. Otherwise, we say it's big. So for small jobs, we can just assign randomly. Using chain-of bound and union bound, you can bound the make span of small jobs by constant times t because of this log n gap. But for big jobs, what we do is we roughly try to assign the big jobs to machines randomly. But if at some time point the node of the target machine is too big, we say that this big job failed to be assigned. So we stop the assignment. We don't assign the big job, and we stop the assignment here, and we do this. And at the end, we consider all the failed jobs and the machines for the failed jobs, and we prove that the components of this graph have small size. Then what we do is we will use the 2 approximation for each component to assign the failed jobs. So that will incur a small cost, a small make span. But the key to generalize, to make the algorithm online is to make this algorithm smooth. So at every time we run this algorithm, but we need to use a common set of random seeds. So we decide the random seeds at the beginning, and we use this random seed for the first time step. We use this random seed for the second time step. Because of the random seeds, they are common. So if you have a small change of x values between time steps, the expected number of changes in the integral solution is small. Yeah, that's the rough idea. Our algorithm is based on an offline algorithm that handles small jobs and big jobs separately. Small jobs can be handled easily. Big jobs, they may fail, but if they fail, we reassign them because the number of failed jobs will be small. That's the offline algorithm. In the online algorithm, we use a common random seeds that will be used for all the time steps. Because of the random seeds, in expectation, the number of changes will be small. Okay.
Any other questions? I have maybe, I don't know whether it's like a silly question. So here you're surrounded to integral solution, but how hard is the problem if you just okay with fractional assignment and you are just balancing max load.
No, that's O1, right? That's O epsilon 1 cost, O epsilon 1 fractional recourse. Oh. Although here, yeah. So here construct a good fractional solution with O epsilon 1 amortized recourse. So that means the total recourse by time t is O epsilon 1 times t. So every job, we will change it O1 times fractionally. So good means it's 1 plus epsilon approximation. So the max span will be 1 plus epsilon times the optimal max span.
And what if you don't allow recourse? Like how? Like I mean, like how? So I'm interested. Like how?
Don't allow recourse.
Integral versus fractional, for example. Like.
Okay, that's a good question. So yeah, we don't know if you can do better than log n. Even for the fractional problem, I think the log n lower bound applies. Yeah, if you don't allow recourse, then we have a tight log m, a competitive ratio, then that holds even if you allow fractional assignment. For fractional assignment, there is still a negative result of log m. Yeah.
Any last question? Or maybe that was the last one. Okay, then thank you again.
Okay, thank you.